It looks quite fun to present the paper, although I haven't, haven't done my classes in this manner, but it seems to be quite fun. And let me add a little bit more explanation to help you understand better. Although, Hyojin explained very well about the overall ideas. So, it looks quite interesting and insightful, and it actually reminds me of some of the techniques called random projection. So maybe 10 or so years ago, there were proliferation, or there were abundant research based on all the linear algebraic techniques in the field of data mining and machine learning. And as you guys know, the projection is basically formulated or represented as a matrix multiplication. So y is equal to wx, where w is maybe 5-dimensional 5-dim vectors, and w is 3x5 matrix, and then w works as a projection that maps 5-dimensional vector onto the 3-dimensional space. And then if we have maybe 3 orthogonal row vectors in this matrix, and then it is called the orthogonal projection. And there are some interesting properties of this. This is not called the orthogonal projection, because the orthogonal projection is requiring the square matrix W that has the same size as the input vector dimension, and then also each row or column is orthogonal to each other. So in that case, all the inner product and the Euclidean distances are preserved. And in the case of these using 3 rows, which are still orthonormal to each other, which means they have a length of 1 for each of these vectors. And then they also have some properties. But typically for this projection matrix is trained or optimized based on a particular criteria. So sometimes it is obtained through the PCA, so that we can maximally preserve the variance, or maximally preserve the sum of all the pairwise distances among our data. Okay, so that is the optimal solution and corresponding linear transformation matrix or dimension reducing matrix. Okay, that has this kind of nice property. Okay, so that is obtained from PCA, but we can just randomly initialize this W and then do some projection onto the 3-dimensional space. Okay, this can be viewed as a random projection. Okay, and then we don't do anything but just randomly initializing this matrix and then do something on that. For example, similar to this work, we can perform the classification or clustering and so on this randomly projected new representation, typically in a lower dimensional space. Okay, so if you search for let's just search for it. And probably some of the some of these papers have more than 1,000 citations, right? So even though the random projection doesn't make any sense, but it will do some useful thing. Okay, and also in this case, probably if my assumption is correct, and then this experiment was done in the following manner. So we randomly initialize this conv structure, whether it is from the RLXNet or VGGNet and so on. We just randomly initialize them, and then we obtain the feature vector at a particular layer, and then do the average pooling of each image. okay, from their activation map, so that we can obtain the yeah, we can obtain the vector rather than the tensor or matrix for to represent a single image. Okay, and then we obtain spatially, globally pooled vector representation of an image, and then we perform the k-means or any other clustering algorithm. Okay, and then suppose we perform the k-means clustering by setting the k as 1,000. Okay, and then and then we create the confusion matrix where the row is a cluster index, cluster 1 and cluster 2 and so on, and then this guy is ground truth 1, ground truth 2 and so on. And then suppose we have maybe 300 data items, and then each data item will have its own cluster index. For example, it is clustered into cluster 37, but it actually has the ground truth label of maybe 5. Okay, and then for that corresponding entry, we just add that entry by 1, starting from all 0. Okay, and then for each entry, we'll have the number of data items that have the specific cluster label and this specific ground truth label. Okay, and then from this confusion matrix, we actually perform this Hungarian algorithm that I just briefly explained. So from this matrix, so this is how the Hungarian algorithm works. So from here, we just simply choose the biggest possible entry, the maximum entry. Okay, and then suppose this guy has the largest element across or throughout the entire matrix. Okay, so that is the most overlapping pair between the cluster and the ground truth. Okay, and then we just extract out such a pairing, okay, between that cluster index and also the ground truth label. And then what we do is to remove completely the corresponding column and row. Okay, and then this was originally 1,000 by 1,000 matrix, and then now after removing this, which is corresponding to like excluding them as a kind of sold out people. Okay, and then we will have 99 by 99 clusters and ground truth labels, and then we do the same thing and then choose the second largest pair of cluster and ground truth, and then we keep doing so until we run out all the clusters and all the ground truths. And that's how we kind of obtain the pairs, mutually exclusive pairs between the cluster labels and the ground truths. And then after aligning them, we can enumerate or reassign the cluster and the ground truth index based on this Hungarian algorithm. So the first one is matching with this ground truth label, and so let's just newly enumerate it as label 1 and also label 1. Okay, and then it's like moving this guy to the top row, okay, the top row, and then moving this column to the top column. Okay, so this guy moved from here, this guy is moved from here to here. Okay, so it's for the second one, and then suppose this guy and this guy was the second pair, and then we will move it to the second row and this guy to the second column, and basically Hungarian algorithm will give an output as a reordered column and row indices. Okay, and then although it's a greedy algorithm, but it will kind of maximize the entries along the diagonal. Okay, because that's how we made a pair and then reordered them with respect to the, so in a way that the first matching cluster and the first matching ground truth is placed on the first row and column, and the second well matching one is placed as a second row and the second column, right? And so this largest entry will be placed over here, and then the second largest entry, after excluding the first row and the second column will be placed along the second diagonal entry, right? So roughly this Hungarian algorithm can be viewed as a kind of greedy approach to reorder rows and columns in a way that the diagonal value and their sum is maximized, okay? Right? And then we can simply compute the accuracy. So in total, what is the sum of the entire matrix? All the elements and their sum is still 300, because we have a 300 data items, and then each of them will add to a particular element, right? So the total sum will be 300, and then in this case the diagonal part and their sum will be maximized, and out of the total data items, what is the diagonal sum? Okay, so that can be viewed as the accuracy after we properly align our unordered kind of clusters with a predefined labels. Okay. So that accuracy is, looks like 12% accuracy, and it's significantly higher than a random kind of initialization or random guessing. And I think, so this random projection has a certain interesting property, and also this the main idea or intuition behind this simple randomly initialized convenes can have significantly higher accuracy than just random kind of assignment is because anyways even if our conv filters are initialized as a kind of random pattern, okay, random pattern, and then we will look for the random patterns across the entire images, and then we will find out where that particular random patterns were strongly found. So that's the meaning of the activation, right? And then in the next layer of ConvNet, and then we will also apply some random pattern, but that so that, I mean, in order for that random pattern to be strongly found, and then it will require a certain kind of combinations of these local patterns within that receptive field, right? And so even though this is a kind of random stuff, but it's not completely kind of random kind of transformation, but it follows a specific structure of like extracting out some local patterns, and then also locally combining those extracted features to obtain these activation values. Okay, so even though these patterns are random, but once performing this kind of convness, and then if the two images have some some meaningful kind of local patterns that are similar to each other, and then that kind of relationships are captured as a result of this convnet output. So I think this architecture itself has a power of extracting out some meaningful features. I'm not sure if it's helpful for you to understand why this should work, at least with this amount, but this is kind of my justification. And in this case, I think most of you guys have understood correctly or properly, but let me add a little bit more explanation. So this is a kind of AlexNet structure without detailed pre-trained parameters. This is just a architecture of an AlexNet or the VGNet, and then this is a randomly initialized one. And then given the feature vector representation, if we apply the clustering, and then it will have at least this amount of an accuracy corresponding to our predefined labels, right? And then given this clustering, and then we can assign each of them a cluster label, right? And then here we do not match our predefined ground truth label yet, okay? But suppose this guy is cluster 1, 2, and 3. So it's completely equivalent to having different assignment of cluster indices 2, 3, 1, but it doesn't matter. Okay, so here let's suppose we obtained this label. Okay, and then we assign this guy as a pseudo label of this 100 and 010 and so on. Okay, using them as a ground truth label, and then we apply just a simple softmax vector. 이게 소프트맥스 벡터를 뽑나요? 이거 맞아요? 이 크라이테리아 이게 소프트맥스로 뭘로 돼 있어요?
그냥 컴포넌트 피처까지만.
네, 컴포넌트 피처를 얻어서 그 다음에 클러스터 레이블을 이 C가 이거 C 센트로이드예요?
네.
Okay. Then I was wrong. So here we don't apply the softmax vector. So here we can obtain the cluster centroid over here, right? And then our last layer is just the image level, kind of globally pooled image level feature vector. Okay, and then we apply L1 or L2 loss, L2 loss, so that so centroid is maybe 4,3. So that's suppose that is our coordinate of the centroid, and this guy seemed to be maybe 3.5, and then maybe what was that? It was 4 by 3, and then it is to the right, and so 4 by maybe 8, and then maybe 2.9. Okay, so this is clearly having a distance from its cluster centroid, and then we want to minimize them. Okay, so that way we want to we are imposing the loss in a way that those green points is closer to its centroid. Okay, and then each of them will have their own centroid, and then this is how this loss function is represented. So because we studied about some linear algebraic or matrix factorization kind of form in the case of k-means, so let's understand this. So C is, so D is the last layer's dimensions, the number of nodes in that last layer, and then K is the number of clusters. So it's basically a centroid, centroid matrix. Okay, so maybe 10 clusters, and then the dimension is 256, and then Yn is just a simple one-hop vector. So Yn is like either having the either element of 0 and 1, right? And then so suppose we have 1 over here in the second dimension, and then it will choose the second column, right? And then what about this guy? What is a 1k? So this is a vector composed of all ones. Okay, so in this case, so this is just a kind of sum to one vector and their constraints. So it's basically representing the sum of the elements of Yn. So Yn is over here as a row vector, and then 1 is just simply composed of all ones. And so what is the inner product? It will be simply the sum of y vectors, right? And then combined with this representation, where each element is either 0 or 1, so it will be just a one-off vector representation. Right? And then at a high level, we give this pseudo label in the form of its corresponding centroid obtained from the k-means performed here. Okay, and then this representation, I mean our loss will actually make all these green vectors as close as possible to each other. I mean towards the centroid location. If it is centroid, and then we will squeeze or make all the green vectors as close as possible to its center or centroid, right? And then suppose this network was updated by one iteration in this manner, okay? And then what would be the next representation? once obtaining the last layer's representation, it will be like, yeah, green values are around here, and maybe blue data items are around here and around here, right? So similar to kind of k-means. So once performing the k-means over here once again, and then the clustering result will almost the same as the previously obtained clustering result, right? So it's like having the exaggeration effect, right? So once obtaining some loosely kind of clustered output, and then we want to make it kind of exaggerated in a way that their cluster boundaries are becoming more prominent, right? So the main kind of driving factor is due to this non-trivially higher accuracy. So even though 88% are wrong based on their clustering result, and then so like somehow this point close to the boundary, okay, so that might be clustered or classified into that part. And so once they are loosely kind of clustered into this blue clusters, and then once just pulling them towards its center so that we can exaggerate this clustering output, and then it will hopefully provide a better matching cluster labels with our predefined ground truth labels. And also here, I mentioned about this self-supervised learning. Okay, so I think this was this is one of the active research area in these days. So if you are familiar with the language model, predicting the next words given the previous words in the domain of an NLP, or like in BERT, we perform the masked language modeling. So in this sentence, what would be the corresponding word that are in this rectangle? So it's probably study, right? Although the sentence is boring, but with the high chance or high probability, we can predict the corresponding verb over here. So predicting this kind of word based on the neighboring words, so that is called the language modeling. And there's a BERT or transformer, and many of these successful and recent NLP models is based on this kind of task setting. And in this case, in a sense that it is a self-supervised learning, because we didn't need any of the labels over here, right? So given the original data as it is, and then we just mask out, or we just hide some of our inputs, and then we enforce our networks to predict that masked or hidden kind of information that we originally have in our input data. So in this sense, it is a self-supervised learning. And then self-supervised learning in the context of an image computer vision, one of the example is a image colorization. So suppose we are given a colored images, and then we can easily make it as a grayscale image, right? And then using it as an input, and then we enforce our network or train our network so that it predicts it's a colored output. Okay, so there is some interesting paper tracking so this is based on the self-supervised learning, which doesn't require any kind of labels for some of the tasks. Okay, so it looks interesting, right? So it's just a set of GIFs, right? And then although we will not discuss about the details on this task, but in this case we just pre-trained our network based on some unlabeled pictures or photos. By that, I mean by the unlabeling, I mean that we didn't have any additional labels, okay, associated with our image, right? But here, the task itself was tracking, video tracking. So like this guy, yeah, we can exactly track like the movement of this car over frames in our videos, right? And then also this ball, we are tracking this ball, right? So it is completely done based on yeah, without any labels, any explicit labels of tracking task. Okay, so it is just doing the colorization task, and then by applying some tricks, yeah, we can perform this tracking task without any labeling data. And also, yeah, jigsaw puzzle is also another yeah, self-supervised task that was used as a pre-trained model for many other tasks. So yeah, I don't remember the details. Yeah, in fact, I haven't looked at that paper at all. But yeah, in the case of jigsaw puzzle, yeah, we can think of like a given, yeah, this kind of an image, and then we just yeah, split them into this patch level, and then we shuffle them down, okay? And then we enforce our network to predict its corresponding yeah, corresponding positions, okay? So in this case, yeah, I don't even know the model details, but yeah, we can apply some pointer network in a way that yeah, we we attach the RNN-based decoder, and then yeah, our decoder should pick up or choose each of these patches in a randomly shuffled order in a way that it first produces or predicts the top left ones and the right next one and so on, right? So we can yeah, design our self-supervision task in that manner. So I think that is a kind of corresponding to kind of jigsaw puzzle-based self-supervised learning, which doesn't require any kind of labeling. Okay, and also another one is, yeah, I really like the paper title, but split brain. Yeah, so Alexei Efros is yeah, Berkeley's professor at Berkeley, and Richard Zhang and yeah, Philip Isola, yeah, these two are kind of inventor of really famous GAN-based models, like cycle GANs and so on. But anyways, yeah, it is also quite simple. Yeah, although I don't remember all the details, but yeah, given a particular image, we just split them into two parts, like top left and the bottom right, and then we make each of them predicts the other, right? So given the input of top left, we make our network predict bottom right, and vice versa. Okay. So in that manner, we can kind of yeah, train our network without any particular label information. Okay, and then in the somewhere in the middle of our layers, then yeah, we can use it as a kind of yeah, good feature representation for some other tasks. Okay, so we apply this kind of pre-trained model to solve specific yeah, tasks such as classification and detection and segmentation and so on. So if you're really creative, and then you can actually yeah, you can actually come up with your own self-supervised learning task. Okay. And also yeah, related to this degradation of the performances at the last layer, yeah, I think the reason is because yeah, let's imagine we trained our model, whether it is a AlexNet or a VGNet, I mean only from their structures, right? And then we performed this kind of task, kind of basically some exaggeration task, right? Until convergence. And then All right, and then yeah, it's just an hypothetical or thought experiments, and might just unproved conjecture. But at each iteration, so let's imagine measuring or evaluating their clustering accuracy by just performing or just by bringing the first iteration output and then apply the Hungarian algorithm with respect to our ground truth label and then compute the accuracy. Okay, and then it will start with the 20%, right? No, is it? Yep, it is, right? But anyways, yeah. And then will it monotonically increase like this? I mean, it cannot increase like this manner, right? But will it monotonically increase? I mean, can we guarantee that? Or can we at least have some reasonable justification to expect this kind of pattern? Probably not, right? So I believe, or my conjecture is that it will somehow kind of overfit, right? So something like this, okay? So it is kind of overconfident, right? So it will keep doing the exaggeration kind of procedures, right? But at some point, I mean, at some point, their matching kind of degree of matching with the ground truth may be maximized, yeah, even before their convergence, right? So it, yeah, although yeah, I haven't observed this kind of patterns, but it is still possible, right? Okay, so if we agree that this is a kind of plausible pattern, okay, so it may not be guaranteed to have this kind of pattern or monotonically increasing pattern, right? So if it is like this, and then we will obtain, or we will just use the converged output for the downstream tasks, right? So in this case, yeah, in this case, this is a kind of suboptimal one, not the maximally or best result. So in this case, I mean, if we admit that this is an overconfident and thus kind of less accurate one compared to the best one that it can obtain, and then with respect to our layers, okay, so layer 1, layer 2, and so on, and then we obtain this suboptimal output, in terms which are kind of less accurate compared to the best possible scenarios, and then somehow L3 and L4, L3 may match better with the ground truth result, right? So that way, it may have like this going down kind of pattern. Okay, this is my hypothesis or conjecture, but I think we don't have guarantees that it will monotonically increase, because it will just pursue their own labels due to their exaggeration. So we don't have any guarantees that their initial guess or their cluster labels are matching best with the ground truth label. Right, and then also related to this, it also reminds me of some interesting paper. So have you heard about, so title is really awesome, prior. Have you heard about it? Consciousness prior. I don't even understand the title itself. It is cited not much, but it's a single author paper by Yoshio Benjio. It was published around maybe 1.5 years ago, and then it was in double column format. 이게 아닌가? 이게 아니네. 이거 후속 페이퍼인데. 이거의 후속. 아, 뭐더라? 이거 연결이 되는데 아는 사람 있어요? 네? 그러네요. 인용한 거 어떻게 했죠? 스칼라?
Experiments on the
Experiments on
consciousness part.
그래요? 제목이 이렇게 좀 덜 안 쿨하지 않았던 것 같은데. 이거요. 맨 처음 거요? 뭔가 팬시한 이미지가 나와야 되는데 이것도 아닌데. 못 찾겠네요. So yeah, we'll have a 10-minute break and then I'll try to find out in the meantime. Okay, so let's resume at 4:57 according to that clock.
갑자기 소프트 다 공부했던
네.
건데 저희가 이미지 비전에서는 이제 스타일을 바꿀 때 이제 그 채널 그 콘도넷 통과시켜 나와 있는 그 피처 레프레젠테이션을 갖고 막 장난을 치잖아요.
네.
뭐 에이다인도 그렇고
네.
그래매틱스 만들어서
네네네.
근데 그런 접근 방식이 혹시 NLP에서도 가능한 건가라는 생각이 들고
NLP요?
네. 혹시 있었나 제가 요즘에는 이제 백 트랜슬레이션으로 대부분 하는데 사이클 캔처럼
네.
근데 이제 만약에 그 가능하면 이제 텍스트에서도 이미의 스타일 변경이 가능한데 지금은 안 되는 걸로 제가 알고 있거든요. 혹시 그런?
네, 일단은 나도 뭐 조금 관심 있게는 보고 있는 게 이게 텍스트 스타일 트랜스퍼 그다음에 뭐 좀 컨디셔널 스타일
네.
트랜스퍼 뭐 원하는 대로
트리뷰트
네 그렇게 하는 게 좀 흥미로운 태스크인 것 같고요. 그다음에 그거를 할 때는 글쎄요. 그러니까 그게 기본적으로는 우리가 그 일단 그 A다인 같은 경우는
네.
그 각 채널별로 우리가 이제 어파인 트랜스포메이션을 해줄 파라미터
네.
각 채널에 있는 각각의 픽셀 값들의 예를 들면 첫 번째 채널에는 뭐 3x 플러스 2를 해갖고 각 채널에 그러니까 그 채널 내 픽셀 값을 3x 플러스 2를 해주겠다라는 그 3과 2. 그다음에 두 번째 채널은 뭐 5x 마이너스 4를 해주겠다라는 5와 마이너스 4. 그 값을 이쪽 그 스타일 이미지를 인코딩을 해갖고 그 값을 얻어내잖아요. A9이.
네네네.
그래서 그걸 이제 그거를 해서 이제 채널별로 이제 어파인 트랜스포메이션을 해주는 파라미터를 우리가 얻게 되는데 텍스 쪽에서는 사실 A9을 쓴 거를 나는 뭐 많이 보지는
그런
못했는데
비슷한 류의 접근은 아예 안 되는 이미의 스타일에 대해서는 좀 쉽지
되죠. 그러니까 그게 사실 이게 좀 그러니까 어쨌건 제너레이트 되는 아웃풋을 우리는 이게 디코딩을 이제 원 에러 타임, 그러니까 한 단어를 하나씩 디코딩을 하잖아요.
네네.
그거는 이제 셀프 어텐션 기반, 트랜스포머 기반의 디코드도 마찬가지예요. 그거는.
네네네.
그러니까 뭔가 한 방에 쭉쭉 하는 건 아니고
네네네.
하나씩 하잖아요. 그러다 보니까 이게 우리는 그러니까 채널이라고 하는 게 그러니까 스페이셜리 이제 서로 다른
네네네,
포지션에
그렇죠.
같은 디멘전에 있는 값을 의미하잖아요.
네.
그러니까 이쪽은 어떻게 보면 디코딩을 했을 때 나오는 아웃풋의 각각의 워드들이 가지는 어떤 레이어의 히든 레프레젠테이션, 그 레이어에 해당하는 레프레젠테이션의 특정 디멘전에 우리가
아,
뭔가 이렇게 동일한 트랜스포메이션, 어파인 트랜스포메이션을 적용해준다는 의미가 되죠.
네네.
근데 이게 약간 이렇게 하나씩 디코딩을 하니까 거기다가 뭔가 조금은 약간 동일한 파라미터를 적용을 한다는 게 아직 다 이걸 생성하기 전에 그거를 따로 이렇게 사전에 만들어서 적용을 한다는 게 약간 조금 맞을까 싶은 생각이 드는데 근데 해봄직하고요. 해봄직하고
마지막 히든 스테이트 쪽에서의 그
네.
파라미터 학습시켜 거기서 좀
네,
변형을
거기서
시킨다는
네.
걸 말씀.
근데 이제 맞아요. 근데 큰 틀에서는 이거를 어떻게 볼 수 있냐면 약간은 어파인 트랜스포메이션이라는 것도 하나의 어떤 심플한 레이어로 정의를 해볼 수가 있어요.
네.
이제 에이다인도 나도 뭐 또 우리 연구실에서 다른 학생들이랑 관심 있게 보는 게 그 어파인 트랜스포메이션 어떻게 좀 제너럴라이즈를 할까? 좀 더
네네.
흥미롭게 만들까의 측면에서 보면 에이다인이 적용되는 어파인 트랜스포메이션을 잘 보면 그 픽셀별로 적용이 되고
네네.
그죠? 그런 측면에서 어떻게 보면 원바이원 컴보 같이 생각이 될 수도 있고
네네.
근데 이제 원바이원 컴보는 이 인풋 채널 모두를 다 뒤섞는 거잖아요.
네네.
근데 이거는 뒤섞지 않아요. 각 채널별로 따로 어파인 트랜스포메이션을 해주는 레이어가 따로 있는데
네.
그러니까 이런 굉장히 간단한 레이어를 우리가 적용을 시키되 중요한 거는 그 어파인 트랜스포메이션 파라미터를 우리가 어댑티브하게 뭔가 우리의 컨디션이라든가 어떤 인풋을 통해서 이 파라미터 자체를 리그레스를 하는 거잖아요.
네네네.
그런 측면에서는 이쪽 그 이제 NLP에서도 LSTM에 해당하는 파라미터들 있잖아요.
네네.
그 인풋, 포겟 뭐 이거 만들어내는 그 파라미터들.
네네네.
그 파라미터들을 예를 들면 이쪽 컨디션에 따라서 그 파라미터 자체를 리그레스를 하는 그런 류의 어프로치들은 있긴 있어요.
아, 그래. 디코단에서.
네.
아,
뭐 있어요.
찾아봐요.
퍼스널라이즈드 NMT니 뭐 이렇게
퍼스널라이즈.
좀 나도 뭐 그걸로 뭐 이것저것 좀 학생들이랑 해보는데 좀 잘은 아직은 좀 안 되는 것 같긴 한데 뭐 팩터 셀 뭐 하여튼 뭐 퍼스널라이즈드 NMT 그다음에 쿼리 오토 컴플리션 뭐 퍼스널라이즈드 쿼리 오토 컴플리션 뭐 이런 류로 좀 내가 일단은 찾아본 페이퍼들이 있어요.
아,
근데
네네.
꼭 그것만이 아니라 무슨 또 메타러닝으로 또 찾아보면 그런 게 많이 나와요. 그러니까 메타러닝이라는 게 결국 이 그때 이제 파라미터를 좀 달리하자 뭐 약간 이런
그때
거거든요. 네.
디코딩 할 때마다.
네,
전원을 탈
디코딩이든
때마다.
아니면 뭐 예를 들면 그 컨디션에 따라서 뭐 그러니까 지금 예를 들면 이게 또 이제 퍼스널라이즈드 무슨 랭귀지 모델링이었나 NMT였나 뭐 그런 게 뭐가 예를 들면 카톡에서 우리가 쓰는 언어랑
네네.
저쪽에서 뭐 쓰는 언어가 있을 때 뭐 예를 들면 이메일 앱에서 쓰는 언어가 있을 때 그거는 이제 서로 다른 랭귀지 모델링이 있어야 되잖아요. 근데
네네.
중요한 건 이거를 같은 랭귀지 모델로 같은 모델로 두고 즉 그 말은 파라미터는 다 똑같대.
네네.
이게 지금 내가 카톡 앱이냐 아니면은 뭐 예를 들면 뭐 이게 이메일 앱이냐라는 것을 뭐 예를 들면 원합 벡터처럼 우리가 추가적인 입력으로
네네.
줄 수가 있어요. 근데 그걸 그렇게 되면 이 원합 벡터는 기본적으로는 애디티브한 성질을 가지거든요. 그 해당 추가된 디멘전에 우리가 이제 닥투백이나 이런 것처럼 이제 그 디멘전에 할당되는 이제 웨이브 벡터가 그냥 그대로 아웃풋 레이어에 더해지는 형태가 돼요.
네.
뭐 그렇게 되거든요.
그렇게 하지 말고 이제.
네, 그렇죠. 그게 좀 한계가 있을 수 있으니까 아예 파라미터 자체를 그 이제 그 카톡일 때랑 이거일 때 다르게 써보자. 근데 이게 다 그냥 따로 쓰면은 이거는 그냥 찢어갖고 이것 따로 저것 따로 그냥 학습을 하면 되는 거거든요. 근데 이거를 나름대로 뭔가 이제 약간 좀 로우 랭크 어프락시메이션 해갖고 뭔가 메모리처럼 그 파라미터의 메모리가 있고요. 그 파라미터의 메모리는 앱은 뭐 한 100가지가 가능해요. 근데 이제 그 우리가 이 파라미터들의 이제 뱅크 그러니까 그 뭐 메모리 셀에다가는 이 파라미터를 10개 서로 다른 버전으로 만들어 놓고 카톡은 이 10개의 어떤 서로 다른 조합으로 이 파라미터를 내는 거예요. 그런 식의
무슨 말씀이신지. 감사합니다. 찾아보겠습니다. 감사합니다.
여기 논문에서 처음에 K에 대한 설정을 클래스 레이블 개수와 동일하게 하나요?
원래는 그렇기가 어려운데 여기서는 뭐 그렇게 했을 것 같아요.
그거보다 더
클러스터.
많아야 되지 않나요? K가?
네?
K가 그 어떤 레이블 개수보다.
왜요?
왜냐하면 그러니까 동일한 레이블 안에 있는 클래스 안에 있는 이미지여도 그러니까 창문을 보더라도 어떤 창문은 이렇게 생기고, 그러니까 얘가 막 그 클러스터링 될 수 있는 게 레이블보다 더 세분화될 수 있지 않나요? 그러니까 다른 클러스터라도 레이블링은 같이 될 수 있지만, 그래서 그 가능성 같은 걸 다 열어보려면 K가 더 커야 하는.
그렇죠. 그러니까 사실 우리가 생각하는 클래스, 프리디파인드된 클래스들에는 한 클래스를 잡았을 때 그 안에 실제로 굉장히 서로 극명하게 명확하게 다른 패턴들이 존재할 수가 있고, 이것들이 다 클러스터로 잡혀야 되는 거 아니냐. 그렇게 되면 한 클래스당 뭐 두세 개, 아니 한 클래스당 두세 개씩 클러스터는 필요한 거 아니냐. 그러니까 클래스가 1000개가 있으면 사실 뭐 한 2, 3천 개를 잡아야 되는 거 아니야. 그 말도 맞을 수 있는데, 근데 또 동시에 그러면 이제 프리디파인드된 클래스 간에 이 한 클래스 내에서 이제 여러 멀티모달리티라든가 아니면 하여튼 여러 좀 헤테로지니어스하게 나타낼 수 있는 성질들이나 패턴들이 있지만, 또 거꾸로 프리디파인드된 클래스들 간에는 또 중복되는 것도 있을 수 있잖아요. 대충 뭐 강아지랑 고양이랑 뭐 대충 네발 동물이다. 꼬리 달린 네발 동물이 뭐 비슷하게 생겼다 그러면 걔네들은 어떻게 보면은 뭐 우리가 하는 클러스터링에서는 같이 또 어떤 측면에서 묶여야 되는 것도 있잖아요. 그러니까 이거는 어떻게 보면 서로 다른 기준으로의 그룹핑을 해주는 거라고 볼 수가 있고,
그러면 그냥
그게 더 실제로 적어야 될지 많아야 될지는 꼭 우리가 1000개를 잡았다고 해서 그 1000개 간에 이제 뭐 내추럴리 나뉘어지는 어떤 명확한 패턴이 없을 수도 있기 때문에 실제 우리 클러스터 개수를 1000개보다 더 많게 잡아야 된다 꼭 그렇진 않아.
그거에 대한 실험은 안 돼 있는 거죠?
그게 이제 뭐 그게 굉장히 좀 캐캐묵은 아니면은 좀 캐캐묵을
그렇죠.
있지만
원래 케민즈를 쓸 때
그러니까 넘버 오브 옵티멀 클러스터 개수를 몇 개로 해야 되느냐 그
뭐,
이슈가 되는 거예요.
결국에 그 이슈.
네네, 그 이슈가 돼서 이제 좀 정답이 없는 문제로 가는 거죠.
알겠습니다.
All right, let's continue. Yeah, I found a paper, which is called the Deep Image Prior. Have you heard about it? Yeah, it is really a cool paper and quite ambitious paper, or audacious paper, or yeah, some brave paper. So yeah, I may have been confused. I mean, I'm not sure whether it is related to consciousness prior at all. Okay, so you can check later on, but at least it contains the word prior. Okay, so yeah, this paper is, yeah, I almost forgot the overall content, but for here, yeah, I really forgot about the details, but yeah, you can look at the paragraphs in this main idea part, but what it does is, yeah, so we basically come up with, yeah, we start with the component and then we train our component. But here, the task itself is really a particular arbitrary task. I forgot about it, what the particular task is. But at least that task is not relevant at all to like this kind of a super resolution or in painting. What is that? Image, yeah, restoration and things like that. Like this kind of super resolution and any other task? Okay, yeah. Anyways, yeah, this task is just doing their its own kind of task, which seem to be kind of arbitrarily set. Okay, and then somewhere in the middle, while they make their model converge to optimally work on their task. Okay, again, this task is a really arbitrary task. Yeah, I mean, particular arbitrary task. Yeah, I forgot about it, but yeah, they introduce some general purpose regularization term. Okay. Yes. Yeah. Sorry. I don't remember almost at all about this. But anyways, so this task is to train their network for a particular purpose, and in somewhere in the middle. Okay, somewhere in the middle. What I mean by that is, yeah, until convergence, suppose we went through like 100 epochs. Okay, and then somewhere in this iterations, for example, like 67 epochs. Once we bring that model, which is not converged one, for their own task, and then this task works really well for a particular task, whether it is a super resolution or in painting. What is in painting? Does anyone know about the in painting? In painting is to fill out the missing values of our image. Like you can think of some kind of a white boxed occlusion. Okay, I think it will show the example of an in painting. Let's see. So this is an example of super resolution. And then, oops. Okay, so this is an in painting example. So we just randomly mask out with the white pixels. So we just hide those information, and then this guy is an image restoration task. Okay, so here and also like super resolution stuff, like given this image, and they add some noise, and then yeah, again these iterations are from some task that is arbitrarily set, okay, with some particular regularization, and then somewhere in the middle of their iterations, then and some step, yeah. So it is a kind of overly corrupted, and I think this one, and maybe this one seemed to be the best one among these different iteration results. Yeah, but anyways, yeah, if you're interested, and then you can read it. And so I felt it is a little bit similar to this work. I mean, yeah, we just train our model for completely different or irrelevant task, and somewhere in the middle of that training process, the model can give us really a good representation for our own task that is completely irrelevant to the main task that is used for training our model. Right, so it is called deep image prior. So yeah, as you saw, yeah, it let's see. Yeah, I mean, yeah, there was an interesting discussions about why and how this should work. Okay, so that's it for this chapter, at least for what I wanted to explain a little bit more. Any other questions before finishing? Okay, then let's get back to our clustering stuff. Right, we studied about this hierarchical clustering, and now the next topic on this clustering is let's discuss briefly about this the quality measure of the clustering result. So basically you can yeah, there are many different measures that you can use to evaluate the clustering quality, but at a high level, they are categorized into two different types. The first one is requiring the external ground truth label, and the other one is not requiring such an external label. So the yeah, in the case of external labels that we use, and then yeah, typically yeah, we can yeah think of the accuracy that we discussed in the previous paper, which is about like the yeah, first we align the pairwise like correspondences between the clusters and the, the ground truth classes, and then yeah, count the relative numbers which can be viewed as a kind of accuracy, right? And another measure which is called the purity. So it is a kind of similar, but this guy is yeah, simply defined as this. So yeah, all the time we can think of these confusion matrix, cluster 1, cluster 2, cluster 1, 2, and so on, ground truth 1 and ground truth maybe 10, for example, and maybe cluster 7. Okay, it is also possible because we do not know in advance the number of clusters, right? Right. So if we have a 300 data items, and then the total number of entries over here will be, will be summing up to 300, right? And here the purity measure is defined as follows. So so let me explain it from this figure. So over here, yeah, let me just give an example of GT2, GT3, GT4, and then 3, 2, 4, 7, maybe 2, 3. So in this case, the purity is defined as this guy. Okay. So how pure is this cluster is? Is cluster. Okay. So simply the relative ratio of the major ground truth class for the given cluster. Okay. So this is defined as this. Okay, so in this case, yeah, let's suppose, yeah, so if we have a 7 clusters, and then we compute this purity measure for each cluster, and then we just take the average of it, and then here was the slight difference from the kind of Hungarian algorithm, and then computing the accuracy is as follows. So in this case, in the case of second cluster and their purity, how is it defined? N5, right? So in this case, it is no longer kind of mutually exclusive. So cluster 1 is paired with the cluster, predefined class 3, and then cluster 2 is also, also matching with the same ground truth class 3. Okay, so yeah, we kind of relax this mutual exclusiveness, or just sold out kind of, so ground truth is never sold out. Okay, so we allow this kind of multiple matchings of the ground truth with each of our clusters. So that is the main difference when computing this purity measure. Okay, and also there are many different measures. Yeah, I forgot the how this computed, but how this is computed. But does anyone know RI? What RI stands for? So it is called a rand index, and in case of an ARI, it is called the adjusted rand index. Okay, so these are some other measures. Yeah, other measures of this comparing the cluster labels, the cluster distribution, and the ground truth classes. Okay, so these algorithms are all working based on this input information of this confusion matrix. Okay, and also you can think of another measure of entropy. Okay, entropy. So entropy can be defined with respect to row-wise or column-wise distribution. So in the case of row-wise distribution, so I mean intuitively the purity measure is how pure the derived or obtained each of our obtained cluster is with respect to their dominant ground truth class, right? And also if we think of their entropy, so if each cluster's data items are distributed over many different predefined classes, and then entropy will be large, and if the entropy is low, and then it means that this cluster, obtained cluster, is a kind of pure, which has a strong correspondence with this, of a small number of or just a single ground truth classes. Okay, so we have this an entropy measure. Yep, and also this entropy and this purity stuff, these are often used as a measure to train some of the traditional machine learning method. Does anyone know what that machine learning method is? Have you studied about the decision tree? I don't think I can find it, but it's really hard to find. And let me just yeah, it doesn't have a good good illustration, so let me try to briefly explain it. So in the decision tree, so we start with the 300 training data, for example, and then suppose x1, so this is a kind of a pair of weight and height, and then this guy is maybe weight is a smaller than 70 kilograms, and at the end of a leaf node, we want to predict it as a whether having a diabetes or not. Okay, so that's the binary classification setting for decision trees, and then here. So given 300 data having weight and height values, as a two-dimensional feature vector, and then how do you obtain this optimal rule that is used for the first node splitting of our decision tree? So in this case, we typically apply the exact same evaluation criteria that we used when evaluating clustering, such as a ARI or RI or entropy and purity and things like that. Okay, so in this case, we can consider the purity as so in this case of a decision tree, we have to choose a single independent variable or single feature, right, and also its corresponding threshold, right? So this is a weight and height, and then we have many different points, right? And then these are the positive ones, and then maybe negative ones over here. Okay, so here, yeah, so we scan through the width and height value and then split them into two parts by applying the horizontal or vertical flips. So for example, yeah, when applying the splitting over here, and then given these two groups, based on our predefined labels or by binary labels, and then we can compute their entropy, for example, and purity as well, right? So we can derive or compute all these different measures, such as an entropy, purity, and so on, right? And then in the case of purity, yeah, we want to find out the best possible purity measures after splitting them into two. Okay, so that is how we train our decision trees. So in this case, so if we have a 300 points, and then what will be the possible splitting of 300 points? So 300 points will be like projected or mapped into a particular x and y value, right? And then we have a way to split them into two groups of 1 versus 299, and 2 versus 298, and 3 versus 297, and so on, right? We exhaustively search through all the possible cases and then come up with the best purity measure. I mean, by that purity measure, I mean that we simply take the average of the purity measure between this group and this group when splitting them into, for example, here. Okay, so in this case, we can choose this best splitting criteria, and that's how we and also so here we can not only split them with respect to first dimension or first feature, but also the second feature as well, right? So here, how many possible splittings are there in this case? So in case of choosing, if we assume we choose the first variable, and then we have 299 different splitting, except for the case generating empty class, right? So we have a 300, and then if we split them into two non-empty sets, and then we have a 299 different splitting, and for each the second dimension we also have 299 splitting cases, right? So among 598 cases, we exhaustively compare among all the different cases and then choose the best one to produce this whatever criteria that we chose. Okay, so this is how we train our decision trees. Okay, so once finding the best one among 598 cases, and then for each of them, and then we have to split their own kind of rules once again, and then for each of the rules, and then we apply the same criteria. Okay, so running this decision trees may sound quite exhaustive, because if we have 100 features, and then maybe 100 features, and maybe 300 data items, and then how many possible splitting by using only a single variable? 100 times 299, right? So there are so many different splitting kind of cases, right? So we have to enumerate or compute all their cases. But fortunately, this may be much smaller. I mean, this different number of possible cases may be much smaller in case we have some of the categorical features. So in the case of categorical features, suppose among the one of these dimensions is maybe gender. Okay, so 1 being female and 0 being male. Okay, so in this case, it is a matter of, there is only one possible cases of splitting based on gender, right? Because in the case of gender, we only have two distinct values, and so splitting them into two non-empty sets will only be just a single case, right? So in that case, yeah, we can have, we can reduce this possible numbers much smaller, into much smaller cases, okay? And also, if we consider this kind of, so in this, suddenly I find out I explained the decision tree training process in detail, but let me continue it, and finish it. So, if we consider some categorical variable, maybe blood types, AB or AB and O, okay? So in this case of a categorical variable that has four distinct variables, okay? So in this case, we can consider their one-hot vector representation and then choose one among them, okay? So in this case, it's like splitting different blood types into one particular blood type versus the three rest, right? If we use a one-hot vector and choose one particular dimension to split, to apply this splitting, right? Does it make sense? But if we just consider this as a single categorical variable, and then what could be our splitting? How many splittings can we apply or can we consider? So we have two sets, and A can be either in this left or right, right? So 2 to the power of 4. Does it make sense? So this is the number of partitioning. Is it correct or not? So we considered, or we exclude kind of empty set, right? So this guy is also 2 to the power of 4 is including the case of all of them is belonging to the left one, but not any of them to the right one, right? So it contains over here, right? So -2 is the actual partitioning that we consider. Does it make sense? 알겠죠? 잘 모르겠으면 다시 설명해 줄게요. 알겠어요? 네.
그 마이너스 2할 때 늦은 것 같아서요.
마이너스요?
네.
그러니까 2의 4승은 이게 둘 중에 하나가 여기 이렇게 되는 거잖아요.
네.
그런데 아까 얘기했듯이 한쪽으로 완벽하게 더 쏠리면 이거를 그러니까 이거를 실제로는 스플리팅을 하는 게 아니니까 이제 한쪽으로 쏠렸을 그 두 가지 케이스를 제외하자는 거죠. 그래서 -2. Right, so decision trees are kind of doing this kind of exhaustive search, okay, and choosing the best possible one with respect to a particular chosen or predetermined criteria, whether it is entropy or Ri or maybe purity and so on, okay. But it looks quite computationally intensive, but it actually is not, because it doesn't have any of the iterative process, right? So there is no iteration, right? So once we determine the best possible one, that's it, right? And also, this is a kind of trick to efficiently train our decision trees. But during during the search process through all the possible cases, to choose the best possible criteria for the first node. And then when considering the second node or the child node, so 300 data items were split into 200 and 100 based on this best possible criteria. And then for this 200 and then splitting them based on all the possible cases. And then somehow those splitting cases were indirect, partially computed from the above case, right? So it is just nothing but a subset of the data that was considered in the first node splitting, right? So I mean, although I don't remember all the details, but you don't actually need to find out the best variable or feature and the splitting value from scratch. You don't need to do so, because most of the computational results were already computed and stored while obtaining the first one, or the best possible criteria for the first node. So we kind of recycle those evaluation results. So that's how we can easily train this decision trees. Does anyone know when to stop the decision tree splitting? So we can split them over and over recursively, right? Oh, by the way, given these two, which one is next split between this guy and this guy? So we don't split them simultaneously, but so we actually consider their marginal or increment performance measure. I mean so in this case we consider the splitting when it was done on this node and that node, and then compare the improvement, I mean quantitative improvement with respect to our predefined measure, whether it is a RAND index or purity measure and so on. And then if that node and then its best splitting criteria is giving the best improvement of our purity measure, for example, and that's the second split. Okay, so this guy will be splitted, and then we now have three child nodes to split, and then for each of them we try out all the possible splitting for each of the nodes, and then choose the best possible criteria and its corresponding node. So these tree growings can be done, is really done in an imbalanced manner. Okay, so it's not like this kind of thing in the case of decision trees. So we kind of like this guy, and then maybe this guy, or maybe this guy and this guy. So as a result, we will have this kind of imbalanced kind of shape or structure of our decision trees. And then so when growing our decision trees, so yes, simply because we keep splitting our node into two separate nodes and further splitting them and further and further and further. And in this case, our purity measure, for example, it will monotonically increase. It will get better and better as we keep splitting, right? Because once this guy had a maybe 75 node arriving at this node, and then suppose this 75 had maybe 40 positives and 35 negatives. In this case, what is the purity corresponding to this node? Is 75 over 40 over 75, right? And then suppose we split them into two, and then 30 by 10 and 10 by 25. Okay, so in this case, what is the purity measure? So 40 by 30 plus 35 by 25 divided by 2, right? So if we split them and then take the average of it, and then that splitting will always increase or improve our purity measure, or whatever defined cluster quality or classification kind of quality. Okay, so in general, given a particular training set, we can grow our trees all the way until each of our leaf nodes has just a single data item, right? So what would be the purity when a node has a single data item? It will be for whatever classification labels it has, the purity measure will be 100%, right? And so all the nodes will have 100% purity, so which is the best possible measures, right? So in this case, yeah, so it is corresponding to kind of hyperparameter optimization. So this is the number of splits, okay? So as we do more and more splits, and then the training error or the purity measure will be going down, monotonically decrease, right? And so we have to somehow stop at some point. And how can we stop? Okay, what is our criteria? It can be based on our validation data and validation data accuracy, or yeah, it can be like this. Okay. But once you go through the code or detailed algorithm of training the decision trees, and then you will have some max number of splitting, okay, max splits, okay. So this is a hyperparameters, so we don't actually do the splitting all the way until each leaf node has a single data item, okay. So we have a maximum number of splits, and then there is another kind of a phase of training decision trees, of rolling back our decision trees, okay. So here, once we grow our trees in this manner, and then we now have the second phase of merging some leaf nodes. Yeah, so here, based on some criteria, if we just determine that, or if we think that these two, merging these two nodes back into the single node is giving the best, best result, and then, we kind of do, we have some certain criteria, and then follow or perform this second phase of a decision trees of rolling back, or merging those leaf nodes back into smaller trees. So at a high level, this decision trees has two phases of growing our trees, and then kind of rolling back into a smaller trees to avoid potential overfitting. Okay. Oh, yeah. And also, among many different evaluation criteria, we only discussed about those requiring external ground truth labels. So purity and ARI or RI, or entropy, and all these measures that we discussed are requiring external ground truth labels. But there are some other types of clustering measures that doesn't require any of the ground truth labels. So that is, that is based on these intra-class and inter-class similarity. So suppose you obtain the k-means, in the case of k-means, so what is the k-means objective criteria? So it is the distance of each point to its corresponding centroid. So that is our objective criteria, and then the sum of it based on all the data that we have, right? So that is the criteria, and that is corresponding to this intra-class similarity or distance, because it is measuring on average, in case of taking the average with respect to the number of data items, and then it will give us the average distance between a particular data item and its corresponding cluster centroid. Okay, so that is called this intra-class similarity or distance. And at the same time, there is also kind of measure, another perspective of the clustering measure called the inter-class measures. So suppose this is a k-means clustering result by using the k as 2, and then here, we can consider, right? So this is a cluster center, and then distance is from is corresponding data items to this cluster centroid, and so on, right? And then we want to minimize this, right? But at the same time, we also have another criteria, or another kind of consideration about the clustering quality, which is the distance between different clusters, right? So if the distance between the two clusters are as large as possible, and then that is considered as a good clustering. Okay, so we have two different criteria. I mean, k-means is only looking at the first one, intra-class distance, and so we studied about the linear discriminant analysis as a classification method for multiple class classification problem based on the generative models, right? But this LDA, or linear discriminant analysis, is actually can work as a linear, dimension reduction method. Okay, dimension reduction method, and here linear discriminant analysis is basically the linear dimension reduction method, which uses some projection axis. Okay, so here, so we have a two-dimensional data over here, and then let's consider some different linear projection direction. So if we use this kind of direction, okay, so this is a kind of projected line, or no, projection basis, and then all these points will be orthogonally projected onto this line. Okay, so here this is an origin, and this is our new axis. Okay, so 1, 2, 3, and so on, and this guy is maybe 4.3 and 4.9, and then each point will have the new coordinate value along this axis, right? And then if we can generalize this guy into higher dimensional space, suppose we have a 100 dimensional space in originally, because we simply have 100 different features, and then suppose we want to reduce the dimensionality into maybe 10, okay, and then we will have 10 different axes. Okay, the first one, and then the second one will be like maybe this guy can be second one, and the corresponding coordinate values will be the second the representation for the second dimension. Okay, dimension reduction method, but I'm not gonna talk about the details at this point. But here, suppose we chose this axis and this axis. So although I explained these two axes as a two different dimensional output, but because this is an originally two-dimensional feature vector, so let's reduce the dimensionality into one. So we either choose this guy or that guy, and which one is giving the better classification separation, better class separation. So in that case, we can consider their intra and the inter-class distance. Okay, so here the intra-class distance is so for example, the red points and centroid will be around here, and then we can consider their average distance after projected onto these this single line. Okay, and then also we will have intra-class distance for the blue cluster. And what is inter-class distance? Inter-class distance can be just viewed as simply the distance between the centroid. Okay, so here the centroid is around here, and then this distance is not that high, right? Right. And then what about this guy? Okay, this guy. So what about the intra-class distance? It seems to be like an intra-class distance is almost the same, but inter-class distance is much larger compared to this case, right? So we have two different criteria, right? So so we can see another example when setting the projection line as this guy, and then we can consider the interclass variance or the distance and the interclass distance between the centroid and that guy as well. Okay, so in this case, which one has a larger intraclass distance? Probably this one, right? Which one has a larger interclass distance between these two? That guy or this guy? Which? This guy? This guy. Left one. Left one. Right one. Right one. Yeah, it is a it is a little bit unclear, but the interclass distance is about this much, right? And then over here about this much, right? So it looks like this guy has smaller interclass distance than this one, right? So that so in terms of a clustering quality or class separation, we want minimum smallest possible intraclass distance, but at the same time largest possible interclass distance. But here that guy is better than this one with respect to intra, but that guy is worse with respect to interclass distance, right? And then so we have these two possibly conflicting criteria, right? So what will be our objective function, or what will be our single criteria? So in the case of this LDA or linear discriminant analysis, we compute their ratio, okay, ratio. So so it's also related to some Rayleigh quotient, but I suppose yep. So yeah, let me just make it at a high level. So intra, yeah, D intra and D inter. Okay, so we want to maximize the ratio between them by carefully choosing W, which is our linear transformation matrix, where we have this guy. So initially we considered a 100-dimensional feature space, and then I mentioned that we reduced the dimensionality into 10, and then at least W has 10 by 100, right? So what will be the optimal kind of solution for this matrix W that linearly transforms the 100-dimensional feature vectors into 10 feature vectors, okay? And then we consider, after obtaining these y vectors, and then we consider or compute their inter and the intra class distances, and then take the ratio of it, and then we want to maximize it, okay? And then it is considered, it is obtained through some something called the generalized eigenvalue decomposition, okay? So that is actually the algorithm for LDA. So once you compute the LDA or run the LDA, it will produce the optimal dimension reducing representation for a given, particular dimension values that will maximize the ratio between intra versus interclass distance. Any questions? 네. 인트라는 크면 클수록 이제 클래스를 잘 나누는 게 되고요. 내가 말을 잘했나? 인터를 맥시마이즈하고 클래스를 이게 약간 인터를 맥시마이즈하고 그래야지 클래스가 분간 아니면 구분이 잘 되니까요. 제일 분리가 최대한 되도록 하고, 근데 분리를 최대한 시킨다는 것도 그 인트라가 워낙 크면 아까 여기 예제에서 그림이 보였죠? 이거죠. 네. 이거는 저거는 어떻게 보면은 네 이게 저거에 비해서 이걸로 보면 인터는 더 벌어진 거 혹은 더 멀어진 것처럼 생각을 할 수가 있으니까 이게 더 좋은 것처럼 보여요. 근데 이게 또 이것뿐만이 아니라 이 인트라가 너무 넓어지면 이게 하여튼 상대적으로 이만큼이 또 지금 겹치고 있잖아요. 그러니까 이제 인터가 더 좁아져도 인트라는 더 좁아지면 되는 거예요. 그러면 저렇게 오버랩이 안 생기는. 그러니까 이제 이 라인으로 이 프로젝션을 했을 때 클래스 세퍼레이션이 이거보다는 더 좋아 보이는 거죠. 그러니까 이게 이제 두 개가 하나는 커져야 되고, 그러니까 인터는 커져야 되고 인트라는 작아지면 질수록 그 클래스 하나끼리는 이렇게 좀 작아지고 인터가 커지면 커질수록 클래스 간의 이제 거리는 멀어지긴 하는데 이거 두 개를 그러니까 두 개를 다 만족을 하고 싶은데 그거를 이제 어떻게 우리는 크라이테리아는 스칼라로 하나로 나와야 되는데 그거는 이제 LDA 같은 경우는 그 비율을 따지는 거죠. 네, 비율을 따져서 그 비율을 맥시마이즈하는 그 솔루션을 베스트 옵티멀 솔루션을 주는 게 이제 LDA고요. 근데 그 크라이테리아는 꼭 그렇게 안 해도 돼요. 그러니까 뭐 인트라, 그러니까 우리가 미니마이제이션 프로블럼을 하면 이제 인트라는 미니마이즈 해야 되고 인터는 맥시마이즈 해야 되니까 인트라 빼기 인터를 한 다음에 적당한 레귤러라이제이션 파라미터를 붙이는 거예요. 네, 인트라 빼기 감마 플러스 인터 그래갖고 그걸 이제 미니마이즈를 하면 그것도 뭐 가능한 어떤 알고리즘이 될 수 있죠. 최소한 이제 오브젝티브 펑션으로서 역할을 할 수 있고 그거는 이제 여기서는 비율을 따졌지만 이제 거기서는 이제 실제 이제 값들의 합을 따지는 거죠. Any other questions? Right. So yeah, we were discussing about the unsupervised evaluation measure of the clustering evaluation criteria. So yeah, basically this clustering has to consider these two aspects, right? So you can consider this a ratio, yeah, rather than optimization criteria, but you can just use it as a evaluation criteria for your own algorithm. So suppose you perform the k-means or some other clustering algorithm, and then you just compute the ratio between them, okay, within versus intra versus inter. So also this is also called within cluster or within class something, and also this is between class something. Okay, so that was about the clustering measure. So now let's move to the Gaussian mixture model. Okay, so the Gaussian mixture model is one algorithm based on this generative model. Okay, although we do not consider kind of classification. Okay. Yeah, in the case of a classification, yeah, we discussed a lot about the linear discriminant analysis, but it is almost the same, except for the fact that we don't have any ground truth labels. Okay, so this is our generation process of our data. So we have some class prior. So if we have two classes, and then suppose this guy is either 1 or 2, okay, and then we have Gaussian distribution for the first one, and we have Gaussian distribution for the second one. Okay, they have their own parameters for each of these two Gaussians. Okay, and the number of Gaussians, or these different numbers that we set, is actually the number of clusters when using these Gaussian mixtures for the clustering algorithm. Okay, and then so what is our parameters to estimate? So here we have, in the case of two clusters, and then it is a Bernoulli random variable, whether it is a 1 or 2, right? So this can be viewed as a prior, like 0.6, 0.6 and 0.4, and this is 1 and 2 for y, right? And then for each Gaussian, it will have the mean value and the covariance, right? And in this Gaussian mixture model, unlike the LDA, where we assume the pooled covariance or the common covariance across all the different Gaussian components, we assume the kind of QDA setting where we have different covariance matrices for each Gaussian. Okay, so that is the initial setting. So at least we know the parameters to estimate in this problem setting, right? So this prior probability, okay, and the mean and the covariance for each Gaussian. Okay, so that's it. And then now suppose we have a 300 data which is represented as W and H, or weight and height, and then suppose they are clustered into like two different groups, whether they have for example, diabetes or not. Okay, I mean, so they are kind of predefined labels, but in the case of clustering, we will just have 300 different two-dimensional feature vectors, right? And then we assume each of our data is generated from one of these two variables, okay? Because you guys know the generation process, where the data item is, in order for the data item to be generated, we first have to choose which Gaussian to generate this data item. So if it was this guy, and then this guy will generate our data item, right? So you can think of it like, for each of the 300 data items, the first one is 1, and the second one is a 1, the third one is 2, and 2, 1, and so on. So you can think of, although we do not know about these values, so they are actually the ones that we have to estimate, but based on or according to our generation process, each data item will correspond to one of these Gaussian Gaussian elements or Gaussian distributions. Okay, and then typically those values, these are unknown random variable that are not observed, right? So these are called ZN. Okay, so Z1 is 1, Z2 is 1, Z3 is 2, and so on, right? Indicating which Gaussian has produced the first data item, second, and the third data item, and so on. Okay, so these are our kind of random variables that were sampled from this Bernoulli distribution. Does it make sense? Okay, so we have some graphical models. Okay, then there are several other good material that explains this Gaussian mixture model and how we estimate or how we solve for the best parameters for our prior distribution and the parameters for each of our Gaussian components. Okay, so that is based on the EM algorithm, expectation dash maximization algorithm. So yeah, so this EM algorithm is really important one. Okay, so that has yeah, that was back in the days that was like a deep learning. Okay, that has produced a lot of impactful or high impact algorithms in many different areas. Okay, and that is also really general, quite general purpose framework that can optimize a given they can optimize a given probabilistic model when we involve some hidden or unobserved random variables like Zn. Okay, so if we assume this is a generation process and then we need Zn, but Zn is not observed, right? What we observed is this X, or this feature vector, right? That is an output of our Gaussian mixture, Gaussian component. Okay, so so this is about the EM algorithm and their high-level description, and let's see if I can do a good job on explaining it. Okay, but here, what is our random variable? Random variable is this Zn and maybe Xn. So for example, Zn, if n was 1, and then the first one is first data item was generated from the first Gaussian, right? And then Xn is the corresponding weight and height value, like 70 kilogram and 175 centimeter. Okay, so this one is known, but this one is not known, right? And also we have 100 of maybe 300 of them. Let's say we have 100 data items, and then we have 100 of them. So we want to maximize their likelihood. Okay, we want to maximize their likelihood given some parameters. Okay, so by the way, this is not a Bayesian kind of stuff. By that I mean, so what is the parameters to specify our generative process or this probabilistic models? First of all, how many parameters do we have in this to specify the Bernoulli distribution? We have 1, right? So the probability of being class 1. Okay, so if we have 3 clusters, and then that will be multi-nully, and the number of required parameters will be 2, right? So we have a parameter over here, and then over here for each Gaussian we have a mean vector, each of which has two-dimensional vectors. So we have 2 parameters for each of them. And then how about the covariance matrix? So we have a different covariance matrix for each Gaussian, and so each covariance will have 3 different parameters, right? Because the covariance matrix is a 2 by 2, but it is symmetric, so we can remove it, right? But anyways, we have this non-trivial number of parameters to estimate. But once we estimated that parameters, and then we can consider the likelihood. So what would be the likelihood? So I mean, this one is an unobserved variable, but let's assume that we know that. Okay, so it is 1. So what is the parameter? I mean, once the distribution for the Bernoulli is like this, and then the sampling 1 from this Bernoulli will be 0.6, right? 0.6, right? Because the first one was sampled from the Bernoulli distribution like this. Okay, I mean, we are assuming a specific parameter theta. Okay, and then 0.6, which is our prior, and then this guy. So if the first Gaussian is having the mean of maybe 75 kilogram and then 173 centimeters, and then some covariance matrices 3141. Okay, and then we can evaluate this guy's likelihood or the probability density value from that Gaussian, and then that value is obtained over here. Okay, this is the likelihood to obtain the first item, right? And then the second item will have the first one, and so on, right? And then we will have a bunch of different probability values that are all multiplied together, right? So this is our likelihood function, right? Right, so at a high level, by using the maximum likelihood estimation strategy or criteria, and then we want to maximize it with respect to what? Data, right? So here, theta is the one to optimize. For example, we take the derivative with respect to, we compute the partial derivative with respect to each of our data values, whether it is a parameter for Bernoulli or the mean for the first Gaussian or the covariance value for the first Gaussian and so on, right? Okay, and then here, do we have an xn? Xn is what we already observed, right? So xn is fixed values, right? So those values are our data samples to perform the clustering on. But what about Zn? Okay, Zn. So this guy is definitely needed or necessary random variable to compute this likelihood, and then maybe once obtaining that likelihood, and then we will just take the derivative with respect to each of our parameters, and then we just set it as a 0 and so on, right? And then that's how we optimize or obtain the optimal variables, right? But here the problem is Zn is not known, right? So we have some unknown random variables. So are these parameters? These are not parameters. They are just a random variables that we need in the middle of generating our data, right? Right, so so at a high level, the expectation maximization algorithm is considering the observation that both involves or both contains observed and unobserved random variables. Okay? And in this case, what we want to obtain or perform is, so here, how about just marginalizing this likelihood? So for example, okay, so even though theta is unknown, but theta is constant, treated as a constant, and then we have some joint density function, okay? And then how about just marginalizing over Zn, okay? And then it will obtain this marginal distribution or density only for observed variable based on or with respect to our parameters to estimate, right? So once obtaining that, and then it will no longer have our unobserved random variable, and then given that expression, we can just perform our optimization with respect to the data, right? Right, and then what's the meaning of marginalizing out with respect to Zn? So of course, right, so this one is not really correct representation. So this bar is assuming that this guy on the unconditional part is a random variable. So if they are considered as a parameters, and they should be written in this form, right? Right, and then what is the distribution to multiply right? So it is a little wrong, sorry about that, but this guy is expectation over Cn. right? So when marginalizing out, we apply this kind of thing, and then okay, and then this guy is represented as the integral of this function to compute the expectation of, and then yeah, and then what, Zn right, right? So this is how we marginalize out Zn with respect to its distribution, right? But in this case, it is also a marginal distribution starting from here, considering the joint at the beginning of xn and zn. Okay, so here, instead of using this, so we use p of zn and xn and theta. Right? So it is like we are doing the expectation with respect to Zn when this Zn is following the probability density where theta is fixed as a particular values, and also xn is fixed as our particular observations, right? Because we already have a particular observations as a axis, or 300 observation vectors like this. So we can only consider the distribution of z conditioned on this specific observation samples or training data, or the data, the feature vectors to cluster. Okay. Right. So we compute the expectation with respect to this Zn when it is following this conditional distribution like this. Okay, and this guy is what we call the posterior, because still theta is fixed, and this xn is now placed in the conditional part. So this distribution is like reversing the order of generation, right? So we first generate the z and the x, but this distribution is reversing this order of this generation, generation of our random variables, right? So we are performing this expectation based on this posterior distribution. Okay. Okay, and then back to this discussion of the EM algorithm. Okay, so we first construct this guy, which is called complete likelihood. Okay, and more exactly, we consider it's a log version. Okay, complete log likelihood. Okay, and then this log likelihood will both involve observed and unobserved variable. Okay, and then from here, given this complete log likelihood, we just take the marginalization. We marginalize out this complete log likelihood with respect to this unobserved variable of Zn, and then it will give us the likelihood of only the observed variable. Okay, in that case, we no longer have z's. Okay, and so we have no problem of obtaining the optimal value of this theta value. Okay, so this is a kind of a big picture of the EM algorithm. And this is not done just by a one-time process. In order to obtain and marginalize out with respect to Zn following this distribution, we actually have to assume a specific parameter theta to marginalize out this Cn, and then it is basically following the iterative process of first marginalizing out Cn's from the complete log likelihood, and then estimate or optimize this theta values. Okay, and then it will basically change this complete log likelihood once again due to a updated data, and then using this updated data we re-evaluate this posterior distribution and then take this expectation operation, okay, and then it will follow this kind of iteration of these two steps. Okay, so again, at a high level, expectation step of marginalizing out unobserved variable and optimizing our variable only based on this marginal distribution of only involving the observed variable. Okay, so that is corresponding to maximization step. Why is it called the maximization step? Because we are just simply applying the maximum likelihood estimation to obtain the parameter value, optimal parameters for this data. Okay, because we have no problem of doing so because we don't involve any of these unobserved variables. Okay, so that way this expectation maximization algorithm or EM algorithm will iteratively perform these two steps. Okay, so okay, then let me continue to explain how this Gaussian mixture model in the context of a clustering tasks is performed. So the first step is, so suppose we obtained this marginalized likelihood function where we don't have this Cn's anymore in our likelihood function. Okay, so again, Zn's are completely determined, so we no longer have these Zn as a random variables, as an unknown values. Okay, so in that case, you can intuitively think of the Cn's are fixed as some values. Okay, and then the next step to update our parameters of Bernoulli and the Gaussian mean and the covariance values or covariance matrices will be identical or exactly the same as linear discriminant analysis. Okay, so these are the corresponding steps. Okay, and then at a high level, this E step of marginalizing out our unobserved variable Zn is basically it's derived as like our Zn's we replace our Zn's by a specific values of this 1 or 2 and so on. Okay, so we replace those Zn's as a specific values, but this Zn is marginalized out, which means we are taking the expectation with respect to this Zn, right? So let's consider this guy, P of Cn given Xn. Okay, so that is the posterior distribution of Zn given a particular Xn and the particular Gaussian components and Bernoulli distribution, right? So in this case, what will be the distribution for this Zn? So at least what is the class of the random variables? What types of random variables does Zn follow? Zn is either 1 or 2, right? Right? 1 or 2 for each data item, right? So it's still multi-nully or Bernoulli distribution or random variable. So this posterior for Z1 given x's and data will be like some distribution over 1 or 2, maybe 0.8 and 0.2, right? So even though we didn't discuss in detail about how to obtain this posterior distribution and also marginalizing out with respect to this posterior distribution from this complete log likelihood, right? But at least this posterior distribution will have some distributions like Bernoulli distribution in case of a 2 classes or 2 clusters, or multi-Bernoulli distribution for more than 2 clusters of a more than 2 clusters in our clustering setting, right? Okay, so here this kind of expectation step is actually boils down to just the replacement of our random variable z as these Bernoulli distribution that was obtained as this posterior distribution. So even though our generation process will assume a single particular Gaussian, so sorry, but the time is up. So anyways, I think I don't think many of the students are following what I'm mentioning, but I'll continue more explanation. I mean, more discussions in the next week about this EM algorithm. But if you have time, and then you can just search for like a EM algorithm and the Gaussian mixtures, and then it will give us a bunch of different tutorials and papers. So I highly encourage you to look at or study those materials, because that will help us understand the next class. Okay, thanks.
주제가 아직 믹스가 안 돼가지고 지금 실험을 되게 많이 하고 있거든요. 그래서 네이버 직원분들께 말씀을 드렸는데 지금 세 분이랑 일을 하고 있거든요.
무슨 주제를?
그 주제가 지금 살짝 안 정해졌어요. 그래서 그걸 좀 정하고 나서 교수님 하는 게 좋지 않을까라고 하셔서.
그래요. 그건 뭐 언제든지 뭐 얘기해주면.
지금까지 어떻게 진행이 됐는지 공유를 일단 캐치업을 해드려야 될 것 같아서 시간 되실 때 교수님 말씀하셔서
알았어요. 그럼 다시 알려줄게요.
행아웃으로 다시 만들어요.
다시 알려줄게요. 그 어그멘테이션 완전한 거를 그건 안 하고 있어요.
그걸 하는 거예요. 데이터
그거 하는 거예요?
어그멘테이션을 하는 거예요.
그거 거기서 하는 거예요?
네.
거기 뭐 약간 뭐 프라이버시 페어니스 뭐 이런 거 하는 거
아니요. 데이터 어그멘테이션으로 로버스트니스를 올리거나 성능을 올리는 걸 하는 거예요.
오케이. 네.
그래서 스타일라이제이션 기법을
알았어요.
알겠습니다.
저희 수업 이거 한 프로젝트 언제부터 좀 시작하는
그거를 다음 주에 내가 이야기를 좀
다음 주에
할게요.
공유.
그러네요. 그 다음 주에 이야기를 하거나 아니면 내가 이렇게 되면 공지사항으로 내가 좀 통지를 할게요.
오늘 발표 해주신 교수님께서 해주신 내용 중에서
네.
그 클래시피케이션을 클러스터로 지금 잡아가지고 했잖아요.
네.
그럼 미스 레이블, 잘못 레이블드 된 데이터를 가지고도 백프롭을 했을 때 그 다음 클러스터를 잡았을 때 더 좋은 성능을 낼 거라고 이야기를 한 것 같은데요. 결과적으로 그랬다? 그러니까 단순하게 그냥
네,
이해해서
맞아요.
그랬다라고 말하기에는 많이 이해가 안 돼서.
네, 그러니까 그게 틀렸을 수도 있는데 하여튼 얘가 생각하는 그 레이블로 그게 마치 트루 레이블인 양 그렇게 아까 얘기했던 것처럼 그런 뭔가 과장을 하는 거죠. 얘가 이렇게 생각하는 게 이게 맞아 해갖고 알고리즘을 끝까지 그냥 돌리는 거거든요.
네.
네. 이게 완벽하진 않아요. 그래서 뭐 당연히 뭐 accuracy가 뭐 이미지나 클래시피케이션 뭐 그냥 레이블 가지 그거 뭐 레이블 가지고 학습했을 때 나오는 그것보다는 훨씬 못 미치죠. 네, 훨씬 못 미쳐서 뭐 한 아까 뭐 킥해봐야 뭐 잘해봐야 뭐 한 30%뭐 이 정도 나오는 건데 그 정도 하여튼 맞다는 거죠. 얘가 이 결과적으로
네.
그러니까 얘 보고 그냥 자유롭게 클러스터링을 해봐라라고 했을 때 예를 들면 1000개로 클러스터링을 하라고 했더니 그 결과를 아까 예를 들면 그런 헝가리안 알고리즘을 통해서 이제 매칭을 시켜놓고 봤더니 실제로 그래서 이 클러스터는 뭐 이 클래스다라고 이렇게 원투원으로 이렇게 이 1000개와 저쪽 1000개 간에 이렇게 매칭을 시켜놓고 봤더니 그랬더니 이제 글씨가 한 30%는 나온다라는 뜻이 되는 것 같아요. 아까 이야기했던 게. 네.
그 정도만 돼도 괜찮은 건가요? 이쪽 필드 자체가 어쩔 수 없는 건가요?
그게 그러니까 뭐 이 논문 같은 경우는 뭐 그게 그러니까 약간 아까 그런 뭐 셀프 슈퍼바이즈드 러닝에서도 이야기를 했던 것처럼
네.
그러니까 이제 그러니까 이렇게 프리트레인드 된 거를 다른 어떤 뭔가 파스칼 VOC는 완전히 이제 뭔가 이미지넷의 1000개 중에 하나로 클래시피케이션 하는 아니 껐구나. 네. 그거랑 다른 태스크잖아요. 그러면 이제 이미지넷으로 프리트레인을 한 게 이제 그 파스칼 VOC로 갖고 갔더니 뭐 그걸 프리트레인드 된 모델로 썼더니 성능이 뭐 예를 들면 한 80%가 나오더라. 근데 랜덤 이니셜라이제이션 해서 파스칼 VOC를 처음부터 트레이닝을 그 아까 뭐 2500개의 그 작은 양의 데이터만으로 뭔가 했더니 뭐 성능이 한 65%밖에 안 나오더라. 그러면 이제 이미지넷 프리트레인드 된 게 뭐 한 15%는 올려준 거잖아요. 65에서 80으로. 근데 그게 예를 들면 그러니까 이 어떤 아까의 그 딥 클러스터에서 한 것처럼 얘가 뭔가 클러스터링을 막 해가지고 얘가 생각할 때 같은 클러스터여야 한다는 거를 강조를 해갖고 그거를 과장을 해서 점점 더 클러스터 거기에 클러스터가 명확해지도록 뭔가 했을 때 이미지넷에서 아까 80만큼 올랐으면은 이렇게 해서 이거는 이제 레이블이 전혀 필요 없이 프리트레이닝을 뭔가 한 거라고 볼 수가 있고 그때는 뭐 한 80까지는 안 나오더라도 뭐 한 72%까지 나오더라는 거죠. 그리고 이제 그렇게 뭔가 별도의 그러니까 레이블이 별도로 있어서 그렇게 이제 이미지넷의 레이블을 가지고 이제 프리트레인을 한 모델은 뭐 성능이 뭐 그 정도까지 나왔는데 이 레이블 하나 없이 뭔가 이 뉴럴넷이 생각하는 그거를 그라운드 트루스 레이블처럼 생각을 해서 그걸 과장을 해서 뭔가 했더니 그렇게 프리트레인한 모델 즉 이제 어떤 레이블도 필요 없이 프리트레인을 한 그 모델의 성능이 뭐 80까지는 안 나오더라도 뭐 한 72%까지는 뭐 나온다는 거죠. 그러니까 아까 그 논문이 그런 측면에서 이제 레이블이 전혀 없을 때에도 뭐 네, 어느 정도는 프리트레인의 효과를 가진다라는 게 이 논문의 뭐 그런 것 같아요. 그러니까 이제 뭐 태스크 자체 세팅이 뭐 말이 안 되어 보여도 어찌됐건 이거는 이제 레이블이 하나도 없을 때 그러니까 랜덤 이니셜라이제이션을 가지고 뭐 파스칼 VOC를 뭐 2500장을 가지고 했을 때는 뭐 65%밖에 안 나오는데 어쨌건 이런 식으로 뭔가 클러스터링이라는 또 별도의 태스크를 두어서 뭔가 뭐 라지 데이터 그러니까 이미지넷 데이터를 가지고 했겠죠 아마도 그러면 그 데이터를 가지고 별도의 레이블이 없이도 그걸 가지고 어떤 형태로든 학습을 했고 그게 이제 딥클러스터라는 아까 뭐 과장을 하는 그런 식으로 학습을 했고 그게 실제로 이제 어떤 타겟 태스크 그러니까 우리가 메인으로 삼는 이 파스칼 VOC 저기 뭐 디텍션이나 뭐 세그멘테이션 태스크에서도 어느 정도는 랜덤 이니셜라이제이션보다는 뭐 훨씬 더 좋은 성능을 준다. 네. 그리고 이제 다른 여타의 이제 셀프 슈퍼바이즈 러닝 어프로치가 있는데 그런 어프로치들이 아까 얘기했던 뭐 컬러라이제이션이든 아니면 뭐 스플릿 브레인이든 뭐 직소 퍼즐이든 뭐 이런 류의 이제 셀프 슈퍼바이즈드 러닝을 통해서 프리트레이닝을 하는 어프로치들보다는 성능이 조금 더 잘 나오더라는 거죠. 뭐 얘네가 왜 그게 잘 나와야 되는가에 대해서는 사실 거기까지는 논리적인 어떤 정당한 어떤 근거는 없을 것 같아요, 나도. 그렇지만 어찌됐건 그런 어떤 레이블이 하나도 없는 상황에서 데이터만 뭔가 잔뜩 있는 상황에서 뭔가 프리트레이닝을 네, 하는 방법으로서 즉 이제 다른 태스크에 접목을 시켰을 때 이제 성능을 올려줄 수 있도록 하는 그런 태스크 세팅에서 네, 얘네께 다른 것들보다는 더 성능이 좋더라 는 거죠.
네, 좀 충격이네요.
네. 근데 뭐 그런 태스크 세팅 자체가 좀 뭐 말이 안 되게 들릴 수 있는데 뭐 그것도 어떻게 보면 연구로서 뭐 그게 뭐 적용될 만한 뭐 상황이 있을 수 있으니까 그렇게 좀 하드한 아니면 그런 데이터가 별로 없는 세팅을 상정을 해서 뭔가를 하는 것이라고 볼 수가 있고 그게 뭐 예를 들면 뭐 나는 좀 비슷한 느낌을 어디서 가졌냐면 뭐 언페어드 머신 트랜슬레이션 그러니까 페어드된 데이터가 전혀 없이도 뭐 머신 트랜슬레이션 시도를 하고 오잖아. 영어 뭐 그냥 100문장, 뭐 한글 뭐 한 500문장 이렇게 있을 때 거기서 그냥 뭐 번역을 해보려고 하는 시도 자체. 그러니까 그것도 사실 어떻게 보면 페어드된 정보가 하나도 없이 그 머신 트랜슬레이션을 어떻게 한다고 그 사람들이 그걸 가지고 뭔가를 하고 있나. 네. 근데 거기서도 연구가 활발하게 되고 있거든요. 네. 그리고 그런 언페어드 세팅에서의 데이터를 뭔가 활용을 해서 뭔가 어떤 태스크를 성능을 올려줄 수 있도록 하는 이런 언스포바이드 태스크, 즉 이제 뭔가 우리가 딴 데서 가지고 올 만한 데이터들은 굉장히 많을 수 있는데 그거에 대해서 우리 태스크를 기준으로 했을 때 레이블이 아직 없는 경우 그런 경우에는 이 데이터를 어떻게 그러면 활용할 수 있을 것이냐 그러니까 마찬가지로 여기서도 이제 그런 식으로 뭐 클러스터링을 통해서든 뭐 뭐를 프리트레이닝을 어떤 형태로든 별도의 레이블 필요 없이 해서 그렇게 해서 나오는 어떤 피처 익스트랙터로서 역할을 했을 때 뭔가 우리 태스크의 성능을 좀 어느 정도 올려줄 수 있다 뭐 그런 측면에서 의미가 있는 거죠.
만약에 적은 데이터, 그러니까 few 데이터셋이 일단 조금 레이블 되어 있는 상태라고 한다면은
네.
그 상태에서 지금 이 방법을 적용을 하면은 어떨까요?
뭐 그게 이제 그러면 이제 세미 슈퍼바이즈 러닝으로 이제 빠지는 거거든요.
네.
그런 것도 뭐 충분히 세팅이 가능하죠. 네. 그런 경우는 이제 뭐
많이들 접근했던 건가요? 그 방법. 그러니까 few하게는 있고
별로 많이는 없어요. 근데 그게 일반적으로 그게 실제로 더 중요한 상황이에요. 왜냐면 내가 아주 소량이든
네.
레이블링은 내가 할 수 있을 테니까
네.
레이블이 아주 하나도 없다라는 상황은 뭐 좀 어떻게 보면 너무 언리얼리스틱 하니까
네.
뭐 내가 10개라도 하면은 되는 거니까요.
네.
근데 그런 식의 연구들이 생각보다는 많이는 없더라고요. 그러니까 이게 현실적으로는 그런 세팅이 대부분이고 이제 언레이블드 된 세팅은 거의 없는 게 맞지만 근데 이제 또 동시에 이제 또 좀 약간 언레이블드 된 세팅에서의 뭔가 연구를 하면 그걸 가지고 성능이 이렇게 오르더라 라고 한다면 그거를 이제 레이블이 조금 있을 때 그때 이제 어떤 어프로치와 합치는 거는 사실 뭔가 좀 조금은 사람들이 그거는 크게 어려운 건 아니다라고 보는 것 같아요. 그러니까 레이블 및 언레이블드 된 데이터가 동시에 있을 때 언레이블드 된 데이터만 있을 때 뭔가 쓸만한 방법을 뭐 그렇게까지 뭐 크게 많이 변형을 가하지 않아도 뭐 그냥 하면 된다. 레이블은 레이블대로 그 기본 레이블로 슈퍼바이즈 하고 얘는 얘대로 뭐 클러스터링은 클러스터링대로 뭐 하고 뭐 사실 그러면 사실 되는 거다. 뭐 두 로스 그냥 합쳐서 적당히 하이퍼 파라미터로 써갖고 하면 되는 거거든요, 사실. 네. 그러니까 이제 그 사람들이 뭐 그렇게 생각을 해서 이제 세미 슈퍼바이즈드 세팅은 또 그렇게까지 많이 또 의외로 그렇게는 안 하는 것 같아요. 나도 세미 슈퍼바이즈드가 실제로는 뭐 네, 퓨어리 언슈퍼바이즈드 언레이블드 세팅은 잘 존재하기 힘들다라고 보는데 실제 연구는 뭐 일단은 이런 것 같아요. 네.
존재하지 않을 뿐만 아니라 그럴 필요가 사실은 없는 거죠. 조금은 더 레이블하고 더 좋은 슈퍼비전 줄 수 있으면
네.
결국엔 성능이 좋은 거니까.
네, 근데 이제 뭐 또 프리트레이닝이라는 게 이제 또 이게 기존에 많이 있는 데이터를 가지고 그걸 가지고 뭔가 기학습, 그러니까 시간적으로 이제 이미 학습을 해놓은 뭔가가 있을 때
네.
그거를 활용한다는 측면에서는 그거를 어느 태스크에 활용할지는 아직 결정이 안 된 거잖아요. 그러니까 우리가 뭐 이거를 뭐 사람 뭐 피데스트리언 트래킹을 하기 위해서 뭐 우리가 갖고 있던 뭐 이미지넷 데이터 중에서 사람을 찾아서 그거를 레이블링을 일부 한다? 뭐 그렇게 할 수도 있겠지만 이제 뭐 저기 뭐 벌트나 뭐 이런 것도 일단은 뭘 할지는 모르지만 그걸 무슨 태스크에 적용할지 모르지만 일단은 그런 언슈퍼바이드 혹은 셀프 슈퍼바이드 태스크로서 뭔가 모델을 학습시켰고 그다음에 그거를 다른 데 그냥 갖다 써라 약간 이거잖아요. 이것도 비슷한 거예요. 데이터셋이 왕창 있으면 이거를 뭐 우리가 하고자 하는 태스크 그거에 입각해서 레이블을 조금 해갖고 이걸 같이 한꺼번에 트레이닝을 하면 된다라는 말은 이제 그 데이터를 갖고 와갖고 이걸 한꺼번에 트레이닝을 하겠다는 뜻이 되고요. 근데 프리 트레이닝이라는 건 어떻게 보면 프리라는 말이 시간적으로 이제 기학습을 미리 해놓는다는 뜻이잖아요. 그러니까 그 태스크 나중에 이제 무슨 태스크 할지 아직 잘 모를 때 그럴 때는 이제 이런 퓨어리 언레이블드 된 세팅에서의 슈퍼비전 아니 그러니까 학습이 뭐 말이 안 되진 않죠. 그걸 나중에 이제 어디다 갖다 쓸지는 모르지만 네.
이런 식으로 클러스터를 기반으로 하고, 그러니까 레이블 온 상태에서
네.
수도 레이블 줘가지고 클래시피케이션 다시 돌리는 방법을 모르는 건 사실은 아닌데, 그게 사실 미스 레이블을 계속 학습시키는 방법이니까 당연히
네.
안 될 거라고 생각을 할 수밖에 없는 상황이었다고 생각을 하는데요. 근데 그게 지금 이렇게 결과가 나온 거라서.
네.
근데 이게 랜덤 이니셜라이즈가 만약 12%가 아니라 뭐 5%였다 이러면 또 안 될 수도 있는 거잖아요.
뭐 그럴 수도 있죠. 그럴 수도 있죠.
그러니까 초기 레이블이 너무 안 맞아져 있으면
네.
안 될 수도 있는 거고.
그러니까 여기서 아까 그 뭐 컬러를 빼고 아까 뭐 소벨 필터 아웃풋으로 갖고 한 게 그 컬러드 된 걸로 하면 그냥 그 컬러 색깔만이 비슷한 애들로 이제 클러스터가 나오기 때문에 그랬을 거예요. 그러면 이제 컬러 비슷한 걸로 뭐 피처 컬러가 비슷한 애들을 위주로 이제 같은 피처가 나오도록 하는 거는 오히려 우리가 무슨 태스크를 하든 썩 도움이 안 될 것 같잖아요.
네.
그러니까 거기서는 그렇게 했더니 뭐가 잘 안 된 거예요. 그러니까 그 소벨 필터니 뭐 이렇게 해갖고 컬러 정보는 죽여서 그 정보는 최대한 안 쓰이도록 뭔가 한 거죠. 거기서도 그런 고충 아니면 애환이 있었기 때문에 아마 그걸 그렇게 했을 거예요. 네, 그러니까 아까 얘기했던 것처럼 뭐 이게 어느 정도는 그래도 좀 괜찮은 스타팅 포인트에서 뭔가 시작을 해야지 뭔가 좀 얘가 아는 거를 이렇게 과장을 했을 때 그게 말이 되는 건데 얘가 처음에 영 좀 뭔가 이상하게 비입을 하는데 그걸 얘가 아는 거를 과장하겠다 그러면 그건 완전 산으로 가는 거죠. 그건 완전 잘못된 방향으로 가는 거죠. 여기서 일단은 뭐 실험적으로나마 그렇게 했더니 뭐 잘 되더라라고 하네요. 네. 네.